Okay, welcome everyone to quantum topology, already part number 7. Yeah, part number 7. I should have used red. Anyway, so we're continuing to do categories, and today I would like to tell you about kind of the main crucial thing that we will see, essentially graphical notation. Graphical notation is around in mathematics for a long, long time, and it's really hard to track it back. So it has been discovered by several people several times in very different occasions. It's one of the things that eventually someone will discover it. And since people don't read anymore, or maybe have never read the literature, they just rediscover it in many, many different occasions, right? So nowadays, really nobody wants to read papers anymore. I guess it was a little bit better 100 years ago. I'm not 100% sure, but it happened very often that certain concepts were just rediscovered several times. And graphical calculus is one of those. It just has been rediscovered by many, many people in many, many instances. And I will present to you the three most popular, at least what I think are the three most popular. And they all do the same thing. And we will explore that in quantum topology in some way or form as well. So the first one, and probably the most popular one, are Feynman diagrams. What they represent is actually not super important. It is of course very important, but maybe not super important for us. More important for us is that there is a graphical calculus presenting something. So so let's have a look at some examples. So I googled here Feynman diagrams, and you see a lot of those diagrams that I will give a name eventually in quantum topology. I will call them webs. We'll see. But for now, just a lot of diagrammatic calculi for very, very different things. Whatever here, for example, whatever these are, right? For very different things, you have kind of the same type of idea. You have a graphical calculus representing some operation. Yeah. And as far as I'm aware, this is actually pretty old. So Feynman diagrams are around for some time at this point. You can track diagrammatic algebra way further back, but this is what I decided to put here as a starting point. And it's like a diagram calculus for certain operations, like an electron and it's a positron, become a photon, and then there will be quark and antiquark, something like that. So some diagrammatic calculus for some process in physics. Really, the only thing you need to know is that there's some diagrammatic calculus describing some non-trivial thing, right? In this case, physics. Yeah, lines represent particles, and vertices represent interactions. And the usual way to use diagrammatics is you take one of them. Here's one, a nasty, not so nice one. Here's another one, and you get a new one by just gluing them together along the common boundary, let's say in the middle, right? So gluing is always like the composition. So you can think of a category of Feynman diagrams if you really want to. Another one, the next one, Penrose graphical notation. Looks very similar, slightly different objects, kind of the same composition, is just stacking or concatenation, and in this case there's some multilinear algebra going on. So people usually think of this as representing certain types of tensors. So Penrose graphical notation represents certain types of tensors, has been introduced quite later than Feynman diagrams, but it kind of does the same. So every type of little symbol here represents a certain type of operation on a matrix, if you want. So here a symmetrization operation on a matrix. So if you look at some images here, so here whatever, a 4 tensor has 4 inputs, a 3 tensor has 3 inputs, something like that, right? The graphical notation for multilinear algebra, right? 3 tensor is a 3-dimensional object, and it's just represented as a little box here in a graphical notation with 3 outgoing edges. And whatever kind of operations, a symmetrizer and anti-symmetrizer, blah, 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 blah. And you can read off whatever type of these type of tensor equalities just from the pictures. Composition is again the same. Similar in flavor, but encoding different things. And the third one are string diagrams for monoidal categories, which is probably what we do most of the time. So string diagrams for monoidal categories. Let's have a look. They have been around also for quite a while. They Feynman diagrams, Penrose diagrams, they're kind of all the same. I think they have been introduced, or at least used, certainly not introduced, but used extensively by Joy Allen Street in the setting of braided monoidal categories. We will see that later on. Well, string diagrams do have this is a Wikipedia page about string diagrams, and the first string diagram appears very far down. I'm a little bit annoyed by that because it's a diagram, but anyway, yeah, those type of diagrams, and if you look at them, they really look very similar to Feynman type diagrams, right? So here, kind of type of a string diagram. Kind of the same. Composition is stacking. And yeah, so this is like, there are a lot of diagrammatic calculi. They always describe different things, but they're always somewhat also kind of the same. And we would like to use these diagrammatic categories, diagrammatic calculi, to describe categories, or certain types of categories, operations in categories. We will actually see what's kind of very powerful language. So what I usually do is the following. I will draw an object as a string, something like that, labeled string. There's an orientation right now. You can ignore the orientation for now. Later, if I have a dual, I use the orientation to point towards the dual, but right now it's just stupid decoration. And I will write a morphism as a state change, right? It's a little coupon that goes whatever from x to y. Right? It's kind of Poincaré dual to the classical notation. And identity morphisms are usually just invisible. I just don't draw them anymore. Composition is stacking, and you have this beautiful theorem that two diagrams are equivalent if they're related by scaling. So right now the calculus is really just one-dimensional. You just stack these diagrams on top of one another. But yeah, anyway, you could have something later like actually going from something like later. Right now we don't have that yet. You can go from x tensor y, which I would represent like that, to z, and you have a way more powerful calculus than right now. Right now it's just very boring, but it's kind of the start of Feynman diagrams. I call them Feynman diagrams, I call them Penrose diagrams, I call them string diagrams. I just call them diagrammatics, whatever you want to call them. And as I said, they have been like rediscovered 1,000,005 times. So it is a very powerful language to think about categories. In particular, string diagrams, the more sophisticated ones later, where we can play tricks like this. So G, you just slide it over, and there's this equality that GF equals FG, something like that. So later, if you have more notions at hand, we can actually do a lot with these diagrams. It's kind of a very, very powerful language in category theory. Anyway, I hope you enjoyed this video, and I also hope to see you next time.